Hello, physical science students. Welcome to a new unit, Unit 3, and this unit will be all about work and energy. Some of the topics we'll be looking at will be work, machines, energy, and thermal energy. This is just a little picture of a cartoon of a Rube Goldberg machine, and you've probably seen these before, but they're just very complicated and complex machines that are designed to perform an extremely simple task, like the self-operating napkin above. So it's just kind of a silly little caricature of a of a complicated machine performing a simple task. So 3.1 is the first section in this unit, and it is all about work. Is this student doing work? Well, contrary to what you might think, in science, this student actually is doing no work at all because work in science is force applied through a distance. So when we talk about work in science, there has to be a force that is applied, like this person is exerting great force. There also has to be distance that is moved. This is a brick wall and it has not moved a millimeter. Therefore, this person is actually doing no work. So the formula for that is work equals F. We designate work by a W. F is for force, capital F, and through a distance. So times distance is lowercase d. So what are the units of work? Well, the units of work are going to be the units of force times the units of distance. What are the units of force? Remember, force is equal to mass times acceleration. Mass is measured in kilograms times acceleration is measured in meters per second squared. So the units of force are kilogram meters per second squared. Kilogram meter per second squared is kind of a long thing to write. So the Newton, abbreviated capital N, is what we measure force in. Well, work is measured in the unit of force, right here, the unit of force is a Newton, times the unit of distance, which is a meter, a Newton meter. Well, again, this is, you can call it a Newton meter or you can call it something even more simple. It's abbreviated capital J and it stands for joules. So work is always measured in units of joules. So let's take a look at force and the direction that the force is applied. And let's look at how that affects the work. Above you see a picture of this man and he is applying a force horizontal, kind of to the right in this picture. Likely this cart is also moving to the right horizontally in this picture. Remember, just keep in mind, force, it really matters the direction that the force is being exerted. Just like it matters what direction acceleration is, because force depends on acceleration. Force equals mass times acceleration. It also depends, acceleration depends on the direction because its components have to do with velocity, and those depend on direction as well. So force is very tied to the direction that the force is being applied. If this man were to exert a force that's maybe this direction, at an angle, what would happen to the work? How would it be different? And you all know that if he was applying force to the cart at an angle like this, it likely would not travel as far of a distance to the right. It is important to keep in mind maximum work is done when force and the motion are parallel. So if there is less distance that is being traveled, then work, it's not as much work being done because work equals force times distance. So when we have force being applied in the parallel, the same direction as the motion of the object, that's when maximum work is yielded. So what about when the force on an object is perpendicular to the motion? So you may have seen this symbol in geometry, perpendicular to. when force is perpendicular to the motion of the object. Here in this picture, this student looks like he's going to study a lot, and he is carrying these books around. His arms are probably getting really tired, and he probably thinks he is doing a great amount of work. After all, his arms are exerting a force that is perpendicular to his motion, right? Here is the force of his arms holding up on the books. Here is the direction of his motion. The direction of his motion is exactly perpendicular, 90 degrees. This is a 90-degree angle. And when motion and force are perpendicular to each other, unfortunately, there is no work done. So there is no work in this situation because force and motion are perpendicular to each other. So let's just take a little review here. When we have the case where force and motion of the force applied to the object and the motion of the object are parallel to each other, we get the maximum amount of work that is done. And we can use the equation work equals force times distance. When force of an object and the motion are perpendicular to each other, however, we have no work done. We just saw that. Well, what about when it's somewhere in between? Like we talked about the guy with the cart. If it's at some angle, let's say we have a force this direction, and we have, or we have a force this direction, we have motion this direction. Here the force would be perpendicular. So here, if we have force this way and motion this way, well, we have zero work. If we have force this way and motion this way, we have maximum amount of work done. What if we have force going this direction and motion going this direction? Well, in that case, you can count yourself lucky because I'm not making you calculate it. It involves a little bit more difficult math. And what you need to know is that when force is applied somewhere in between parallel and 90 degrees to the motion, it is basically yielding work that is greater than zero and less than the maximum amount that could be gained if the two were parallel to each other. So if the force and the motion are somewhere in between this parallel and 90 degrees, it will be somewhere between zero work and maximum work done on the object. Here are some ideas for advanced proficiency, lots of fun. Why was the unit of work, the joule, named for Mr. Joule, James Prescott Joule? What about this, too? If you're interested in math, if you like math at all, the complete work equation is actually force times distance times the cosine of theta. So if you have done any of this yet in math, or if that looks interesting, look at why this equation reduces to work equals force times distance when it's applied in the same direction as the motion of the object. You can show me. You could even make up some little problems and show me how much work is done when we actually have an angle in there between the force and the direction of the distance of the motion of the object. So look forward to seeing you in class.